Cassava roots arrive by the ton, but the factory doesn't see food. It sees a high-purity carbohydrate feedstock that can be converted into textile-grade polymer with tight control over odor, color, and molecular weight. Every truck is weighed, sampled, and logged by farm and harvest date. BECAUSE cassava chemistry shifts fast after digging, and that shift changes starch yield and fermentation performance. The first engineering problem is dirt and cyanogenic compounds. Cassava carries soil, sand, and peel residues that foul pumps and wear stainless. It contains cyanogenic glycosides that can release hydrogen cyanide if mishandled. So the line starts with aggressive washing in rotary drum washers and spray tunnels. It's followed by destiners and rock traps that protect the grinders downstream. Water runs counter-current to reduce consumption, and turbidity sensors tell the system when to refresh or filter the loop. Next comes size reduction to expose starch efficiently without turning everything into fines. Knife cutters and rasper mills shred the roots into a wet mash. The goal is to rupture cells while keeping fiber fragments large enough to separate. The factory controls rotor speed and screen size because too much shear raises viscosity, increases filtration load, and steals starch into the fiber waste stream. Starch extraction looks like mineral processing because it's separation by particle size and density. The mash is diluted and pumped across vibrating screens and rotary sieves that catch coarse fiber, while the starch-rich slurry passes through. Hydrocyclones then take over, spinning the slurry so heavier starch granules migrate outward and lighter solubles move inward, creating a concentrated starch stream in multiple stages. This cascade is tuned for recovery because a single percentage point of starch loss becomes huge at scale. The extracted starch is washed to reach textile-grade purity. Residual protein, pigments, and soluble sugars can create yellowing and odor in the final fiber. So the plant uses multi-stage countercurrent washing with conductivity and pH control. Dewatering happens through centrifuges and vacuum filters, producing a clean starch cake that feeds the conversion line. While the extracted fiber and peel residues head to a byproduct system, that byproduct system is not an afterthought. It's part of the plant's economics and energy balance. Pressed pulp is sent to anaerobic digesters to make biogas for steam boilers, or dried for animal feed, depending on local markets. Wastewater is screened and treated for high cod loads, because starch-rich effluent can overwhelm treatment. If it isn't managed with dissolved air flotation and biological reactors to turn starch into fabric, the factory must first turn starch into a fermentable sugar. Starch is long chains of glucose, so it's liquefied and saccharified using enzymes in heated stainless reactors. Alpha malus breaks the chains into shorter dextrins under controlled temperature and pH. Then glucoamylase finishes the job by converting dextrins into glucose syrup. Inline refractometers track solids content. An enzymatic conversion is optimized to maximize fermentable sugar while minimizing byproducts that would complicate purification. Now the process shifts from separation, engineering to biochemical production. Glucose syrup is pumped into fermentation tanks where selected bacteria convert it into lactic acid. The building block for a common bio-based textile polymer, polylactic acid, or PLA. These reactors are run like chemical plants with dissolved oxygen control, agitation profiles, and temperature regulation. Because fermentation rate affects both yield and impurity formation. Antifoam dosing is automated, and off-gas is monitored for flow as a real-time indicator of metabolic activity. When fermentation reaches target concentration, purification starts, and this is where premium fabric is won or lost. Lactic acid must be stripped of color bodies, salts, and residual sugars that would cause polymer discoloration and brittleness. Filtration removes biomass. Ion exchange columns remove ionic contaminants. Activated carbon polishes color. And vacuum evaporation concentrates the product without excessive heat that could create burnt notes. Each step is monitored by conductivity, UV absorbance, and ash content. Because polymerization is extremely sensitive to trace contaminants. Polymerization converts lactic acid into long chains with a specific molecular weight window needed for fiber spinning. First, lactic acid is dehydrated to form lactide, a cyclic dimer. In reactors that control temperature and residence time to prevent unwanted side reactions, then lactide is purified by distillation, because even small amounts of water or residual acids can terminate polymer chains and reduce strength. Finally, ring-opening polymerization builds PLA in a melt reactor with catalyst dosing and vacuum control. And the output is tested for melt flow index, residual monomer, and color. Before spinning, the polymer is pelletized, dried, and conditioned. PLA is moisture sensitive at high temperature. and moisture causes hydrolysis that chops polymer chains and destroys fiber strength. So pellets are dried in desiccant dryers to very low dew points. Moisture sensors verify dryness continuously, because one wet hopper can create an entire run of weak filament. Spinning is where polymer becomes fabric-grade fiber. In its high-speed fluid mechanics inside micron-scale holes, pellets are melted in extruders with multiple temperature zones and precise screw profiles that stabilize melt pressure and minimize thermal degradation. The melt passes through screen packs and melt filters that remove gels and unmelted particles, because a single gel can snap filaments and shut down an entire spinning position. The filtered melt enters a spinneret, a metal plate with hundreds or thousands of capillaries that shape the filaments. Pumping is done with precision gear pumps that hold flow rate constant, because filament diameter depends directly on volumetric throughput. The filaments are quenched with controlled airflow that solidifies them uniformly. And quench air temperature and humidity are tuned to prevent sticking and to set the initial crystalline structure. Those filaments are still weak until they're drawn. Drawing stretches the polymer chains into alignment, increasing tenacity and stabilizing shrinkage. Multi-stage Godet rolls pull the yarn at carefully defined speed ratios. The factory targets a specific orientation to balance strength with softness. Heat setting follows because PLA's thermal behavior is different from polyester, and the plant uses controlled hot rolls or ovens to lock in structure, without causing excessive crystallization that would make the fiber harsh to create premium hand feel. The plant manipulates filament count and cross-section. Microfilament spinnerets can produce extremely fine filaments that feel softer against skin and drape like silk, while shaped capillaries create trillable or hollow fibers that change luster and moisture transport. Texturizing units then add crimp and bulk using air jets, which improves cover, stretch recovery, and insulation without adding weight. Staple fiber lines take another route. Continuous filaments are bundled into tow, crimped mechanically to mimic natural fiber waviness, then heat set and cut into staple lengths compatible with cotton spinning systems. This allows blending with cotton viscose. or recycled polyester to tune breathability, durability, and cost. While keeping a bio-based content story, quality control runs in real time because spinning lines produce kilometers of yarn per hour. Laser micrometers check denier uniformity, tension sensors detect filament breaks, and camera systems spot fuzz, gels, and contamination. Lab tests measure tenacity, elongation, shrinkage, and dye uptake. Because fabric mills need predictable yarn behavior at high loom and knitting speeds. From here, the yarn becomes fabric through knitting or weaving. Warp beams are prepared with uniform tension to prevent bar and streaks. And sizing chemistry is selected to be compatible with PLO so it doesn't embrittle the yarn. Knitting machines run at high RPM to produce jersey and interlock fabrics used in daily wear, while weaving looms produce tighter constructions for shirts, linings, and structured garments. Asterisk dyeing and finishing are engineered around polymer sensitivity. PLA has different dye affinity than cotton or polyester, so dye classes and temperatures are chosen to build color without deforming the fiber. Jet dye machines circulate fabric through pressurized dye liquor, and pH and temperature ramps are controlled to prevent shade drift. Heat exposure is managed carefully, because excessive temperature can cause PLA, shrinkage, or loss of mechanical properties. Finishing turns raw fabric into wearable performance. Calendaring controls smoothness and luster, while mechanical brushing can raise a softer surface for comfort. Functional finishes, like hydrophilic treatments for moisture management, anti-odor chemistries, or loaded as softeners are applied with pad cure lines, where pickup percentage is measured by weight gain and controlled by knit pressure. The factory aims for finishes that survive laundering without blocking biodegradability claims. So chemical selection is driven by both performance and regulatory compliance. The Cassava 2 fabric claim stands or falls on traceability and mass balance. Digital lot tracking ties each fabric roll back to the starch batches, fermentation runs, and polymerization lots, with records for impurities, moisture, and spinning conditions. Many plants run third-party audits to verify bio-based content and restricted substance compliance, because export customers demand proof, not marketing. Energy and water efficiency determine whether this process scales economically. Heat integration captures energy from condensers and evaporators to preheat incoming streams. And variable frequency drives on pumps and blowers match power draw to throughput. Closed-loop water systems reuse wash water after filtration and treatment. And the largest plants design wastewater handling around high organic loads from starch and syrup residues. What makes this factory high-tech is that it connects agriculture, microbiology, polymer chemistry, and textile engineering into one continuous specification system. Cassava starts as a wet variable root, but it exits as filament diameter. Yarn strength, fabric drape, and color fastness, metrics controlled by sensors, recipes, and feedback loops. The result is a premium fabric built from a renewable crop. Engineered through fermentation and precision spinning, produced at the scale required for clothing that people wear every day.